Hey everyone, welcome to this video. Let's talk about the transformer encoder. So here is our current knowledge of transformers. We have input tokens, which will become word embeddings. These will be passed to positional embeddings, which will remember word order because attention does not inherently remember word order. We have to give it to it. Multi-head attention measures similarity for words to get context-aware word embeddings, as we can see up here. And we want context-aware word embeddings because ultimately they give us better output. However, multi-head attention only does linear transformations. As we have learned in the activation functions video in this course, for the model to learn complexity, we need non-linearity. So, pass the output from multi-head attention to a fully connected feed-forward neural network, as we can see here. And we have already reviewed what this is earlier on in the course, so this should not be a surprise to you. And this diagram is a quick refresher, right? Perceptrons move from left to right. And in the fully connected feed-forward neural network, there will be hidden layers that will use a ReLU activation function, and that will give the model nonlinearity. Next up is layer normalization. Similar to what was discussed in the data transformations video from earlier in the course, if the values passed to the model are too big or too small, performance can suffer. So we want a sweet spot. Normalizing these numbers to a specified range can help with performance. So quick review, right? We have standardization and normalization. Although I find normalization more intuitive to understand, where you update values to a range of 0 to 1. So let's say we have three values, negative 1 million, 79,000, and then positive 1 million. After normalization, negative 1 million becomes 0, 79,000 becomes 0.5395, and 1 million becomes positive 1. So again, this is pretty intuitive to understand, I think, normalization. And again, normalizing these numbers to a specified range can help with performance. Layer normalization can be done at different steps. So one example, we can put layer normalization after multi-head attention and after a fully connected feed-forward neural network. Or we can put layer normalization before multi-head attention and before a fully connected feed-forward neural network. Now, here is our understanding of an encoder layer so far. And it's getting a bit crowded. So let's simplify this to a rectangle that just says encoder layer. And what we can do is use multiple encoder layers, like let's say 3, stack them up, and ultimately the output is still context-aware word embeddings. If you're asking yourself, why do we want multiple encoder layers? The answer is a model with many layers is needed for learning complexity, right? But even though we need more layers to learn complexity, there's going to be two issues that can arise. Issue 1, a model with many layers, gradients are more likely to rapidly shrink, vanishing gradients, or rapidly grow, exploding gradients. And as we discussed earlier in the course, vanishing gradients and exploding gradients will cause issues with your model learning. Another issue is that a model with many layers can lead to information decay. What do I mean by this last part here? Information decay. In this contrived example, let's say that when the input goes through these 3 layers, we'll use a random number. Let's say there's a 10% decay or like a 10% information loss. So only 90% of the input information will be saved or preserved, which isn't the worst thing in the world. But if you do 0.90 times 0.90 times 0.90, after layer 3, only about 73% of the original input information is still intact, so to speak. So how could we overcome this information decay, so to speak. Let's use a residual connection as a way to skip these layer computations with the 10% decay each. So here's the residual connection, which you can almost think of as like a shortcut. Then add the input with the output, as we can see here. The residual connection helps save input information and, less obviously, reduce vanishing gradients, because gradients will also use the residual connection. Okay, so here's our final understanding of a transform encoder. As you can see, we do encoder layer 3x. Here are the residual connections. So quick review again. Positional embeddings, remember word order. Multi-head attention measures similarity for words to get context-aware word embeddings. Fully connected feed-forward neural network will give the model nonlinearity. Residual connections and layer normalization, which are two new concepts we have both learned in this video and in this course. The TLDR and in summary, they both help a complex model perform better. All right, that's it for this video. Thanks for watching.